Okay. So we're going to continue our exercise to compute actual scattering amplitude of string theory using our master form. At the end of the last class, we understood how to compute correlation functions on the sphere for the BC system, and we were beginning to compute correlation functions for the XCFT. Okay. So first, let's look at the following. Suppose I've got product I equal to 1 to n e to the power I k mu x mu. Suppose I want to compute this object on the sphere plane. Okay. This is actually very easy to compute. Let's quickly do it. Well, there's 20,000 ways of doing it, but one way is just to remember what the Lagrangian is. Okay, so we had our action was e to the power minus 1 by 4 pi x prime del x squared, and then we have this I k mu x. Now, what you have to do in order to compute this, what you have to do is to complete the square. Right? So, we're going to do it in a slightly cumbersome way by actually computing the saddle point solution, because we're going to need it for the insertion downstairs. So, what was the saddle point solution? What's the equation of motion? The equation of motion from varying this is del square by 2 pi alpha prime x mu plus I k mu x mu of sigma I equal to 0. Right, so the minus of this has gone in the minus of the and this actually extra factor of 2 is because of the two things together. Okay? Now you remember that del square by 2 pi x mu, del square by 2 pi of log of sigma minus sigma delta is equal to delta of sigma. This, I've got the path integral and I've got an insertion. It's a Gaussian path integral, so I'm going to solve it by just substituting the on-shell value of the action. Okay, so this is the equation of motion, as you said, and I'm reminding you that del squared by 2 pi on log gives you delta. Just to remember where that came from. Suppose you evaluate del squared in polar coordinates. So the first r that you take a gradient of it, you get r hat by r, and then you Gauss law integrate that. That gives you a 2 pi. Right. So that's the 1 by 2 pi. Okay. And so we get, using this, that the solution is that x mu of sigma.
Index structure of the equation.
Index structure of what?
That equation is.
This equation?
Yes.
Yes, this one is. Right, thank you. So we get
because sigma is not being integrated.
Correct.
No, that's it.
Sigma. Thank you. Thank you. Okay. And so we find that x mu is equal to, so let's see, minus I k mu. Then we get an alpha prime here. So minus I alpha prime k mu divided by sigma minus sigma I. Sorry, times log. Log of sigma minus sigma I. Sum over all sigma I. So this should probably be k mu. Is this clear? I'm writing it again more clearly. X mu is equal to minus I alpha prime sum over I k mu I log of sigma.
Shouldn't be a minus sign in the equation?
No, there shouldn't, because there was minus sign in the action. And when you integrate by parts, you pick up another mass.
Gaming also considers this is overall.
What?
Minus is overall also.
No. This is the insertion. This is the e to the power ikx insertion. Okay, not that. We have better.
I'm sorry, is there a denominator in that equation?
No, there's not. That equation is just going to be written up here. Okay. And so we've got that x mu is this object. Now, first let's use this to evaluate this simple way. You see, one way of doing it, I'm doing it very cumbersomely, just because this cumbersome method will prove useful when we actually have the insertions downstairs. Okay? So, but one way, of course, of evaluating any Gaussian integral is just substituting the solution to the equation of motion into the action. Okay? So, what was the action? The action was e to the power plus 1 by 4 pi x mu del squared x mu. Plus because they're integrated by parts. Okay? And then plus I k mu sigma, k mu of x of sigma. But we know that del squared of x mu by the equation of motion is equal to this object. Okay, so del squared of x mu is equal to this object with a factor of 2 pi alpha prime. Okay, so had this extra 2 not been there, this guy would exactly have cancelled this guy. Okay. Because the factor of 2 is there, all that this does is say that this on shell is the same as e to the power I by 2 k mu x of sigma sum over I. Now in which we have to substitute what x of sigma is. Okay? So we have e to the power I by 2 k mu I, and then x of sigma I was up there. So there's a minus I alpha prime, sum over j, let's call it k mu j, log of sigma j minus sigma I. Sigma I minus sigma. Okay, so x of sigma I is this formula. Is this clear? And this whole thing was always summed over sigma I over I. Okay, so now this formula gives you two kinds of terms. There are the terms with I equals j, which are problematic, because you have log of sigma I minus sigma I. Those are the terms that, of course, are renormalization throws away. Those are the terms that come from self-contractions. Okay, those will go away. I'll come back to those terms in just a minute. I'll just give you an intuitive explanation of something. But let's forget that for a moment. For the other terms, we've got I times minus I, so that's 1. We've got a half, and then we should sum over all pairs, so that summation over pairs kills the half. So we get e to the power k mu I dot k mu j. So ki dot kj with an alpha prime, sum over pairs. Okay, so where the sum now goes over pairs. So taken away the half, which is the same thing as sigma, let's call this zij mod to the power alpha prime ki dot kj. Is this clear? This is dot product over pairs. Okay? And of course, if we did this with the care that we should. What we have not taken into account here carefully is the integral over the zero mode. Okay. And the integral over the zero mode will tell us that there is a delta of sum over k. The momentum conserving delta. Okay, just because zero mode vanishes from here, but appears in this as k times x0. So the zero mode, the entire dependence of the zero mode is e to the power summation of ki times x0, and doing the integral over the zero mode will therefore give us the delta function. Okay, just momentum conservation will be ensured by the sum of the zero mode, by the integral over the zero mode. Okay, so this is the final answer. This is the final answer. This is the final answer with where the insertions are just e to the power 8. Any questions or comments about this?
Sir,
Yes.
why did we call that equation the equation of motion? Because it's the action plus the insertion.
So it's the equation of motion in the presence of these forces. So we've got an action plus insertion, and now we've got Gaussian integral. Vary that. Don't call it equation of motion. Okay. Is this clear? Okay. Now that's great, but this has also allowed us to compute these expectation values with the insertions of del x's in the denominator. Why is it done that? Because you remember what our rule was. The rule that we reviewed last class is that if you've got insertions downstairs, you have to replace them by what the value they take on the solution to the equation of motion on the saddle point. Okay, plus fluctuation fields whose contraction is governed by ignoring the source term. Those fluctuation fields are just fluctuations of the x's, ignoring the sources. Okay, so suppose we had an expression like del x mu downstairs. So that should be replaced by what it was on its solution to the equation of motion. So what was the x on the solution to the equation of motion? Look at this object here. So if we want del x, we could write this as log of mod z squared by 2. Okay, and then that's z minus z tilde into z bar minus z bar tilde, and then differentiate. So we will get del x mu goes to minus I alpha prime by 2 k mu I over z minus z I. Del x mu at some point z will go to this. Okay, and of course everything is over 4/9. Okay, if the insertion point was a zi, was one of the insertion points of these, which it will always be, because our vertex operator will always have an e to the power atx times something at the same point. Then once again the summation goes over all values of I not equal to j, because the self contractions that gave you that term at I equals j are removed by our renormalizations. Okay, so del x mu of sigma j is equal to minus I alpha prime by 2 sum over I mu I by sigma j. What is it? That here. This is the term that is just evaluating what this object was on the equations of motion. Okay? And in addition, of course, In addition, of course, we replace this by a fluctuation. Plus del x tilde. Where the contractions of the fluctuation field are now evaluated in the action without the e to the pi k dot x. Okay? So the rule for computing these correlation functions here. Is this rule clear? Say that downstairs insertions get a piece that comes from the e to the pi k dot x upstairs, because e to the pi k dot x is a big thing. Because it's an insertion in the exponent. It changes the saddle point. Things downstairs are small. They get contributions from the change in the saddle point, plus the fluctuation, plus the fluctuation contractions. Is this clear? We're going to use this rule repeatedly. If there's anything confusing about this rule, you should know.
Fluctuation, contraction.
Fluctuation, contractions. What was our, what was our rule? You remember last time we analyzed this simple e to the power minus x minus a all x squared, and then we had some f of x. Okay. And then what we said was that, well, let's write this as f of x minus a plus a. Okay? Then we will change your variables. X minus a is some x prime. So this is equal to minus x prime squared f of x prime plus a is just whatever this object evaluates to on the solution, on the saddle point. X prime is something that's still whose expectation values you still have to compute. But we have to compute it in the action without the shift. Okay? So that's what we're doing. We're taking the insertions, writing them as insertion plus fluctuation. Insertion evaluated on saddle point, that's like A, plus fluctuation. And then the x primes have to be Wick contracted using the usual rules. It's just that they are now independent of the k's. Is this clear? Okay, excellent. Fine. Now, before this is all we need for computation, but there is an interesting conceptual point today that's sort of interesting to discuss. It has to do with the self-contractions. Okay, we have been using this sophisticated normal ordering prescription to compute the diagrams that removes all self-contraction. But suppose we were being less sophisticated. Suppose, we were just computing a path integral. We wanted to regulate that path integral and then renormalize it. Okay, how could we proceed? Now, the kind of infinities that we're getting is because we're getting Green's functions of one point sitting on top of another. Okay? So, if we sort of smear out the Green's, and the problem with our Green's function is that the Green's function is divergent when 1.6 is top. Yeah, the norm. So suppose we did something interesting. Suppose we define a regulated Green's function. Okay? Suppose we define a regulated Green's function as follows. G of sigma minus sigma prime is equal to, what was it, minus alpha prime by 2 log of sigma and sigma prime squared for sigma minus sigma prime less than epsilon. Okay? And then this was equal to minus alpha prime by 2 log of epsilon squared, is greater. Sigma minus sigma prime less than epsilon. This would be a regulation of the Green's function. Okay? And you might think we can proceed with this. But there's a problem with this regulator. And the problem with this regulator is that it violates diffeomorphism. Why does it violate diffeomorphism then? It's because if we have an arbitrary metric, so let's say that we've got a metric that we fixed up to y factor. Okay? If we've got a metric that is flat, the flat metric times times Y factor. Okay, we're not allowed to put some cutoff on coordinates. What we are allowed to do is to put some cutoff on invariant distances. No, but yeah, so your cutoff will have to involve the Y factor. Okay, so what we're allowed to do if we want to be diffeomorphism invariant is to say that the metric, that the Green's function gets cut off. Okay, when the invariant distance between 2 points goes smaller than epsilon. That is the diffeomorphism invariant. Okay, now what is the invariant distance between 2 points? If the coordinate distance between 2 points is epsilon and the Y factor is e to the power phi, let's say, then so that the metric G mu nu is equal to e to the power phi times eta mu. Let us suppose that was the case. Then the invariant distance between any 2 points, okay, so the invariant distance between any 2 points is epsilon times, let's call this 2 phi, epsilon times phi. Let's say delta x times phi. Coordinate distance times e to the power phi is the physical distance between 2 points.
But your metric need not be in this form at all.
Let us suppose that it is. Okay, we've used diffeomorphism invariance. Let's say that we've done the kind of thing that we do. We've used diffeomorphism invariance to put the metric into Y factor times the standard form of the metric, like we've been doing.
We can't always do that. You have one line on it.
Okay, it need not be a flat standard form. On the sphere it is. It's true. I'm trying to give you an intuitive explanation. Don't probe too hard. Okay. All this can be taken back off. Right? This is the main point. We become this delta x times e to the power phi. Okay? So, now, what was the cutoff? We're allowed to say that suppose this is less than epsilon, the Green's function should change. Okay? And so that's when this delta x is less than epsilon e to the power minus phi, the Green's function should change. After which, what should it become? So for delta x, so suppose we had that, so now let's try round 2. G of sigma minus sigma prime is equal to minus alpha prime by 2 log of sigma minus sigma prime the whole thing square. Let's say, okay, for sigma minus sigma prime square greater than epsilon e to the power minus phi. And then for those values when it's lower than this, you replace it by this, by sigma minus sigma prime at cutoff, which is this. So you replace it by minus alpha prime by 2 log of epsilon squared e to the power minus 2 phi for sigma minus sigma prime less than epsilon e to the power minus. You see? So, now you've got some log epsilon square which you can renormalize. But you've also got some y dependence elements. Now, what's log of e to the power minus 2 phi? Let's keep track of the y dependence. Okay? Log of e to the power minus 2 phi. Log of e to the power minus 2 phi, this object here is just minus 2 phi. Now we multiply minus 2 phi by minus alpha prime by 2. Okay, so it becomes alpha prime by times phi. This whole thing is multiplied by ki dot ki and was all in the exponent. you see here is that an insertion of e to the power I k dot x, which classically is while invariant, actually quantum mechanically picks up a dependence on the while factor. What is the dependence on the while factor? It's e to the power alpha prime k dot k times phi. So it behaves like this operator has a weight. This operator is behaving like it has weight under while transformations, equal to e to the power alpha prime k dot k. Okay? But remember that alpha prime k dot k, that this alpha prime k dot k was precisely the scaling dimension of this operator. Alpha prime k dot k by 4, we had factors of 2, right? In every given segment. But that's the scaling dimension of the operator. And you remember that we had on general grounds deduced that any scalar operator, okay, that has non-zero scaling, that is a diffeomorphism scaling, okay, that has a non-zero scaling dimension, has this because of its transformation under while transformations. So we knew that this operator e to the power I k dot x transformed under while transformations in a way governed by its scaling dimension. You work out on the fact that it is precisely this. We see this now in an intuitive way. The intuitive way one way of saying it is that if you try to regulate the theory in a way that is diffeomorphism invariant, that will force you to pick up while factor dependencies in insertions of e to the power k dot x, precisely in a way to account for its transformations under while transformations, which is what gives it its scaling dimension under conformal. Okay? So this is meant to be an intuitive explanation of something that we've already argued more sophisticatedly. Is this clear?
To start with, why do you just consider it's just diffeomorphism invariant? You can start with while invariant.
You see, diffeomorphism, while the transformation under while properties is a physical property of the thing, we're going to regulate the theory in a way to maintain diffeomorphism invariance and see how everything transforms under while transformations. You see, there's no problem with this thing picking up a weight under while transformations. It just means that the operator had a dimension. Okay? So while transformation is an invariance under while transformations. It's an outcome, it's not something you put in. Okay, but diffeomorphisms, of course, we've got quantum field theory to regulate the way, preserve this diffeomorphisms. Okay, any other questions or comments? Okay, good. So let's go. Let's move on. So now we've understood the rules for how to compute these contractions of vertex operators in the scalar set. Okay, before we actually start computing lots of scattering amplitudes, I want to now very quickly introduce open strings. So far in this course we've been talking about closed strings. Many of the easiest scattering amplitude calculations are actually done for open strings, because you have to do half as much work. You don't have left and right movers. Okay? And so for that reason, it's a good time to quickly discuss open strings. There's not much to it. Is it?
That's the kind of terms that you get log of x squared, which are defined and you add additional counter terms in the latter.
You have to renormalize the operator. It's not the Lagrangian thing. So you would define the operator as, you see, e to the power k dot x times e to the power minus k squared epsilon. So that's the actual insertion you put. So that cancels this. Notice that you're getting these funny things, these funny infinities only at the location of the operator itself. So by renormalizing, but you see, this is the general rule, right? What is an operator insertion inside quantitative? It's an insertion you put inside your path. Now that insertion that you put inside your path integral, if taken literally, usually is infinite. As we've seen many times, x square is just infinity. This includes contraction of x with x, which is infinity. So you have to define your insertion. We defined it in one nice, careful way using this normal order prescription. What we're now doing is discussing another way to define such operators. Okay, to regulate and then renormalize. So your actual insertion would be e to the power k dot x times e to the power epsilon squared times 1. Is this clear? Okay, great. Okay, other questions, comments? Okay, so now let's turn to a quick discussion of the opus. We've been talking about strings which live on a cylinder. Okay, and they're just periodic functions of the spatial coordinate of the cylinder. Now you could ask, could you instead look at strings which live not on a cylinder but on a string? We're going to take the coordinates of the strip to range from 0 to pi. Okay? Now, of course, if we're going to do this, we need boundary conditions. It's just the classical evolution of the string. If you don't have boundary conditions, you don't know how the differential equation is not sufficient. Right? For instance, you've got a term of the differential equation which is del square. You take the string, you discretize it up into little points. What does del square here mean? It's not a complete problem unless you specify boundary conditions. Okay, now what kind of boundary conditions are we going to specify? Well, we're going to try to specify boundary conditions that are consistent with the action principle. Okay, boundary conditions such that the variation of the action continues to give us del square x equals 0 as the equation of motion without additional dynamics of the boundary. Okay, that's very easy to do because you see what was our action? Our action was equation. Our action was this, and in order to get the equation of motion, we needed to integrate by parts. Okay, we've got a boundary in the sigma direction, so it's the sigma integration by parts that's of interest. So we have del sigma x, and we get the variation to be del squared of x times delta x plus, of course, a total derivative. The total derivative term, so suppose this was the delta x, was del sigma of delta x times del sigma x. That was the total derivative, so it just is this object evaluated at the boundaries. Okay? If we want that total derivative to vanish, if we want this piece that's in the variation of the action to vanish, we basically have two choices. Either we can ensure that delta x is equal to 0. This would happen if you put Dirichlet boundary conditions. If you said x at the boundary was something fixed, then you can't vary x at the boundary. Or you can leave x at the boundary free. Okay? And put the boundary condition that del sigma x at the boundary vanishes. Now, if x was something specific at the boundary, that choice breaks Lorentz invariance. Because it's a choice of x. Okay? Actually, this boundary condition, the choice that x being something specific at the boundary, will turn out to be very interesting when we come to study debriefs. Because there will turn out to be nice, interesting, solid tectonic states in string theory, which do break translation invariance, and whose effective description is given by putting Dirichlet boundary conditions on open strings. So the boundary condition delta x equals 0, namely x equals something fixed, will turn out to be of great interest to us in what follows. But that will be of interest to us in studying excitations, in studying solitonic excitations of string theory. We postpone that to the future. At the moment, we're interested in Lorentz invariant background of string. Lorentz invariant string theories. Okay? So that leaves us with basically one option, which is to put the boundary condition del sigma is mu is 0 at every boundary of our string. Okay? I've said del sigma because I was looking in this language. Of course, the covariant generalization is that this is the normal derivative of x as you approach the boundary vanishes. Is this clear? So we're going to study open strings strings that live on a strip subject to these boundary conditions. Okay. We're also going to insist. Okay, really. Okay. So now, what are the solutions to the equations of motion of string theory? We're just looking to solve del square x equals 0. Well, we know that it has to, our spatial profiles have to be such that the derivative at 0 and pi vanish. That works if we choose cos n sigma. Okay? So cos n sigma, and then when you actually solve the equation of motion, there'll be two types of time dependencies here. E to the power I n tau and e to the power minus I n tau. So the full set of solutions to the classical equation of open string theory are cos n sigma with an e to the power I n tau, or cos n sigma with an e to the power minus I n tau. Okay? Now, for many purposes, it's useful to think of the open string as just the holomorphic sector of the closed system. And I'm going to try to explain that now. Okay? See, cos n sigma is e to pi n sigma plus e to the power minus I n sigma. And let's choose one of these time lengths. That's e to the power. Okay, and then we get right. That's our solution. Now look at this solution. This solution has a path that behaves like sigma plus tau. That's this guy. And a path that behaves like minus sigma plus tau. So it's got a left moving piece and a right moving piece. Okay? And this whole solution lives between 0 and pi. Now what I'm going to do is the following. What I'm going to do is to define a new function y such that y of sigma tau lives in sigma belongs to 0 to 2 pi. Just like a closed string. Okay? So y is going to be defined. So given the x's, I'll break this up into x left and x right. Okay? And what we have is that x left is equal to x right at both sigma and pi. As you see from here, or you see just directly from the differential function. Because x left was x of tau minus sigma, x right was x of tau plus sigma. Okay? So if you demand that x left, you've got some x left plus some x right, and then you differentiate with respect to sigma at sigma equals 0. That differentiation picks up x left prime minus x right prime, because x right was a function of tau minus sigma. Okay, so we get the condition that x left prime minus x right prime is equal to 0 at sigma equals 0 or at sigma equals pi. Okay, and if I have two functions, the derivatives are, equal everywhere up to a constant, they're just equal. Okay, so up to some 0 more business which we take out. Separately, the left and the right parts are just equal.
The derivative argument you gave just says that y is a currently the smooth function, right?
Why? So far now you talked about y. I'm going to, yes, y will be a sigma.
No, like the basically derivative argument you gave only works on the boundaries. Right?
Only on the boundaries. So x left is equal to x right, and sigma equals 0 and right. Otherwise they're completely, yeah. Okay. So now the function y that I define, y is going to be xl of sigma for sigma belonging to 0 to pi. But y is going to be x right of 2 pi minus sigma for sigma in the range belonging to pi to 2 pi. So y is it. Okay? Now see. Firstly, x right of 2 pi minus sigma is a left moving function. Because it was a right moving function of tau and sigma, but then you replace sigma by 2 pi minus sigma, so it becomes a left moving function. Okay? So this definition gives you a completely left moving function on the plane 2 pi, 0 to 2 pi. Moreover, this left moving function is smooth because where we're patching things up. Okay, so let's say sigma equals pi. This is x left of sigma. It's also x right of sigma. X left of pi. It's also x right of pi. And x left and x right had to be equal to each other at pi. That was a boundary condition. Similarly, at sigma equals 0, at sigma equals 2 pi, we get x right of 0, which is the same as x left of 0 by a boundary condition. And therefore, what this gives you is a smooth periodic left moving function, a single smooth periodic left moving function. Okay? So we say that sewing together the left moving sector with the right moving sector turns this function that lives on the strip into a purely left moving function that lives on the cylinder. For this reason, the open string, for many purposes, is like one half, it's like the holomorphic sector of the closed string. Okay? And the calculations of the open string actually are often easier than doing calculations with the closed string. Okay? I have to tell you also about the boundary conditions on the coasts. Okay, so we have coasts, of course, that live on the strip. The coasts also obey boundary conditions. Now, where do the boundary conditions come from? They come from the fact that we will only look at those coordinate transformations that will not change 0 or pi, will not change the locations of the boundaries. Okay? So what was our C field? Our C field was the anti-commuting form of an infinitesimal coordinate transformation. Okay? So what we want is that C sigma is equal to 0 as sigma equals 0 and pi. Okay? But C sigma is basically C plus minus C minus with some factor of 2. Because C plus, remember what plus was? Plus was tau plus, x plus equal to tau plus sigma. And x minus is equal to tau minus sigma. So tau plus sigma minus tau minus sigma is 2 sigma. Okay, so this is proportional to this with some factor of 2. So if you want this to vanish at the boundaries, what you want is C plus and C minus to be equal at the boundaries. Once we move to Euclidean, C plus becomes C, C minus becomes C bar. Okay, so what this tells you is that C is equal to C bar at the boundaries. That's the boundary condition for C. Okay, I'll leave it to you as an exercise to work out that you get the same boundary condition for B. It's similar in the respect. Okay, so once again with the boundaries, B is equal to B bar, C is equal to C bar. Okay? And now, once again we can define a master C field. You see, the master C field is defined exactly like that. It's equal to C of sigma from 0 to pi, and C bar of 2 pi minus C from pi to pi. This master C field is purely left moving. Similarly for B. Okay. So once again, for the ghosts as well, working with the open string is like working with a purely left moving sector potential. Okay? And of course, when we actually do calculations, we take this strip and conformally map it to the plane. More precisely, we took the cylinder and conformally mapped it to the plane. What happens to the strip when we conformally map it? So our conformal mapping took us to Z, which was e to the power tau plus I sigma. Okay? If sigma is restricted to 0 to pi, where on the Z plane do we land up? Above plane. The argument lies between 0 and pi. So the real axis, the real Z axis, okay? The real Z axis becomes the boundary of, is the conformal mapping of the boundary of the open string, and the real Z axis is the boundary of the open string. This is where our thing, where all our fields live. Okay? Finally, what is this doubling trick? What is this doubling trick in the Z plane? So the doubling trick should be that we get a field in the whole Z plane. Because if you had a field in the whole cylinder and you conformally map it, you get a field in the whole Z plane. Okay? So let me say it in the context of, let's say, the C first. It's very simple. It's simply that, you see, it's simply that you define the master C field, which is equal to C of Z in the upper, and is equal to sigma of Z star in the lower plane. Okay? You see, C bar was a function of Z bar. Therefore, C bar of Z star is a function of Z. Okay? So, this gives you a completely analytic function. Okay? Was the function smooth? Well, at the boundaries, the boundary is the real axis. Is the real place. At the boundaries between these two definitions, C is equal to C bar. That is about definition. Okay, so it's just smooth. Where they match, where they patch together. These guys are smooth. Are equal?
They are also relating to derivatives.
No, just C is C. Okay. Now, of course, the whole thing is analytic. Let's see. You see, the point is that you have a first order equation of motion for this constant. Okay? So, if you've got a first order equation, the value of a field here, just the value at one slice, completely determines the value everywhere else. That's the data for the differential equation. So, we've got a first order field such that the data for this differential equation here and here agree. So, this generates something here, this generates something here, and then you've got a uniform equation. So the whole field just means the equation del Z C bar is equal to 0. So it's fine. It's automatically.
That works the classical level.
That works at the classical level. Right. All of this here is, all of this is a trick. It's just, if you prefer you can work with the fields C and C bar, they're distinct fields, they have, What I'm telling you is that if you got some object, that is, whose correlators will be effectively analytic. Okay? You get all the same correlators by just considering this master field and not worrying about any jumps on the boundary. Why? It's because correlation functions of these guys obey the classical equations of motion. Okay? So within insertions and within the path of table, all of this will be. But anytime you feel uncomfortable, you can unpack it. Okay? This is just to help make things faster. Okay? So now suppose you wanted to find, you wanted to compute correlation functions of the C and C bar. You just use the master formula that we already know for C. 1 over is Z12, Z13, Z23, and then put in your replacements. Okay? Clear, right? Excellent. So, okay. I suppose, but by the way, the doubling trick for the X fields has similar consequences on the Z. Right? The same thing. Upper plane, lower plane. One holomorphic field in Z, effectively. Okay? But
what is it that you have to specify apart from if you are patching two functions across two regions? Just specifying that the value for the two functions is the same and the boundary is not enough. You're saying you have to specify the derivatives as well.
Well, it depends on the equation. You see, the functions, if you just specify, you could be doing mathematics or you could be doing physics. You could be looking at functions that obey equations of motion.
Yeah.
If you're looking at functions that obey a second order differential equation, okay, then saying that on a patching surface, the function degree is not enough. Because you see, you can take that surface and the value of the function, the first derivative of that, right? And then that gives you the equation. That evolves this way. Okay? Similarly, that way. Now, if your equations of motion are compatible, okay, so if you have then you have the same data for this evolution and this evolution, you get a smooth function. Okay? But you have to have the same data, so you have to specify both the function and the first time derivative. If you've got a first order equation, that would be sufficient. Just the function would be sufficient. In our particular case, at least on solutions of equations of motion, if you feel uncomfortable with anything, just work out the cosines. Right? It's what I'm saying is just totally obvious. At the level of the cosines, you're just taking part of the cosine and then the other part of the cosine and closing it out. And the cosines are nice and smooth. Okay, there's nothing deep here. It's just some GQ. Okay, great. So now what we're going to do is to start. It's one last bit of irritating formalism, and then we'll actually start with computations. The last bit of irritating formalism is now we're going to need to compute. We're going to need to compute in the X CFD. In the present, if we're doing computations for, if we're doing computations with open strings, we're going to need to compute. Correlations in the present in the CFD with this on the upper half plane with some boundary conditions, and possibly insertions at the boundary. So let's think about these insertions at the boundary for a minute. Okay? Let us remind ourselves why we're computing these insertions. We're computing these insertions because we're computing string scattering amplitudes. Okay. Now, how did that go? A string scattering amplitude was related to an insertion because of the state operator. And how did it go for closed strings? We had a cylinder, okay, and the state operator patched that up into part of the plane, with an insertion. Okay. Now suppose in this setup, we had a strip, because that's what an open string is. Okay? And now we apply the state operator map to this. Do you see that this will close this up into this, but with an insertion on the boundary? Do you see that? Okay? Closed string insertions, these guys gave you an insertion in the middle of that disk, whatever it was. And that disk could have been anywhere. But this thing can only emerge from the boundary. And so it will turn into an insertion on the boundary. So scattering of open string states will map to inserting operators on the boundary of this upper. Okay, so we need to specially consider insertions on the boundary and see if there's anything conceptually new that happens. Okay, so suppose I've got now, suppose I've got two insertions in the upper half. Okay, and I want to compute the 2-point function. So suppose I've got x of z1, I've got an x here. Okay? I want to compute the 2-point function. I want to compute the 2-point function of the 2-point function of x with the path integral, which is e to the power minus del x, the whole thing squared, 1 by 4 pi alpha prime. But on this space where we're imposing the boundary conditions that we are. Okay? And what are the boundary conditions again? The boundary condition is that the normal derivative of x is 0. Let's say this is this upper half plane language. What is the normal derivative? It's the y derivative. Okay? How do you get y derivative from z derivatives? Okay? So z is equal to x plus iy. Z bar is equal to x minus iy. Okay? So y derivative will be z derivative minus z bar. Okay? So del z of x will be equal to del z bar of x on the boundary. That's our boundary condition. Okay? So I want to know what is the Green's function? What is the 2-point function? The Green's function for insertions of x with these boundary conditions on my boundary. Okay? Now, as we know the Green's function, you can replay the computation of the logic from the Schwinger-Dyson equation if you want. The Green's function is in the end the solution to the equation del squared on g is equal to delta function. Except that the Green's function now has to obey new boundary conditions. Okay? So what we have to do is to solve the equation minus del squared by 2 pi alpha prime g of sigma minus sigma prime is equal to delta of sigma minus sigma prime. Or delta of right? We have to solve this equation subject to the boundary conditions that g del z of g is equal to del z of del z bar of g at the boundary. Okay. Now we had earlier said that the solution was let's see. We had earlier said that the solution was I'm not sure if we wanted it with this plus or minus. writes the answer with a minus. So here's the equation. So okay, good. What's this? Okay, so we had earlier said that the solution was alpha prime by 2 log of z minus z prime square. Okay, but now if we take this object and we differentiate it. Okay, now if we take this object and we differentiate it with respect to z, we'll get 1 over z minus z prime. We differentiate it with respect to z bar, we get 1 over z bar minus z bar, right? Okay, and at the boundary z is equal to z bar, but z prime is not equal to z bar, because z prime is not a point at the boundary, right? So how do we deal with this? We deal with this in the way that we deal with this in the electrical mechanism. So the problem is that what we've done is that we're solving for the source, like we're solving for solution del square phi with a source here. If we add an unit charge underneath, okay, that will then automatically ensure that our boundary conditions are maintained. And you might ask, well, but then it's not solving the same equation because we've got a new source. Except that the new source is not in our domain. We live in the upper half plane. So we can just in our minds add the image charge. That will give us a function that is analytic everywhere in the upper half plane. So it will not change that the upper half plane's equation is solved. But it will, okay, so let's say that more carefully. So what's the solution here? The solution is minus alpha prime by 2 z log of z minus z prime square times plus log of z minus z bar z prime bar square. Now let's check if our boundary conditions are okay. We differentiate this, we get minus alpha prime by 2, we differentiate with respect to z, 1 over z minus z prime, plus 1 over z minus z bar. Now, on the real axis, z is equal to z prime. Okay, if we differentiate with respect to z bar, what would we get? We get minus alpha prime by 2, 1 over z bar minus z bar prime, plus 1 over z bar minus z prime. On the boundary, z is equal to z bar, so these two are the same. Right? This is very simple. So the image charge method gives us very quickly the solution to the Green's function of interest.
We have to split both ways or just one way?
What?
We have to split both ways or just one way?
No, just one guy, just the source. You should think of this as follows. You should think of it as you are doing del squared on z with a source at z prime. So if you add a source at z prime and a source at z prime bar, then the solution of that automatically obeys your boundary.
Okay, so I'm doing related with xz prime. Couldn't I also think of z as a source?
You could. Actually, see, all that matters, because this thing is z, what is this mod z square?
This is the same thing.
It's the same.
I see.
So you don't write.
In the other point we are taking it z bar because we are working with Euclidean theory and z bar is same as x now. Because if you want to reflect it, you don't want to take x.
But I'm using bar and star interchangeably. Bar means complex boundary of the mind.
That's because we are working with the Euclidean theory.
But sorry, maybe I should just have said star. What I mean is complex conjugate. I've got a point and a complex conjugate. We're just doing solving a mathematics question. We need to put the source at z and the source at its complex conjugate. That's all. Sorry. Okay, in my mind, there's no difference between bar and star for the purpose of this. Okay, great. So now
boundary state, the boundary state, that only reflected or being.
Very good. So if you have a boundary state, that will not be reflected. No. So what? Yeah. So suppose we got an extra source at the boundary. Okay. So what we're going to do is to think of that as the limit of this when z prime hits the boundary. So of course you just get 2 of the same term, but you do get the extra factor of 2. Okay, so the Green's function when you go to the boundary is just the limit of the Green's function in the bulk. Okay, and that's going to be very important. Okay, so now let us in particular look at the thing that will be particularly important for us. Namely, you see, because we're computing open string scattering, all our insertion points will be at the boundary. So suppose Z and Z prime were both boundary points. It was Y. So they're both real boundary points. Okay? So now this correlation function becomes what? The Green's function becomes minus 2 alpha prime log of 1 minus y. Because both these terms are just the same. Both mod squares, so that gives a factor of 2, and there are 2 such terms. Okay, so from half alpha prime, we go to minus 2 alpha prime. Okay? This actually tells us something serious as well. Okay? It tells us the following serious things. Suppose we wanted to compute correlation functions. Suppose we wanted to compute the correlation function of boundary insertions at the boundary. Now we're going to have to normal order our operators to subtract away the singularities when 2 boundary points approach one another. So those singularities will be associated with this Green's function. Okay? So we define a boundary as the fun symbol uses. Y of sigma, y of sigma prime. This thing is defined as y of sigma, y of sigma, y of sigma prime minus this insertion, minus 2 alpha prime log of y minus y. Okay? Points in the bulk, we normal order in the same way. You subtract away the 2-point boundary norm. Okay? The net result for computations will be just use this effective Green's function and ignore all self-functions. Because the boundary normal ordering is defined so that you will ignore all self. Okay? Now, so suppose we want to compute insertions of x's at the boundary. Now what will you get? Okay, so we want to compute insertions of x's at the boundary. So if we wanted e to the power k I x times e to the power I x sigma I, and suppose that was a product. Okay, suppose we wanted product over I if I k I mu x mu I. What is this evaluate? Okay, now we're going to do it. We have to do it. Really, what we should do is repeat what we did at the beginning of the lecture. We'll take a shortcut so we get the answer fast. Okay, you see, there is a general formula for this in terms of Green's functions. The general formula is that this is equal to e to the power minus k mu I dot k mu j into x mu sigma I x mu sigma j. Product I ij and by 2. one way of, this is just coming from completing the square. One way of remembering the factors is to Taylor expand this. Okay? So if we Taylor expand this guy, we should get the first term in that should give us the Taylor expansion of this. Okay? So let's Taylor expand this guy just to check we got the factors right. Okay? So the Taylor expansion will give us I k mu x mu squared by 2. I just Taylor expand those guys. Then I have to take expectation value, so I'll get my x mu expectation value. The by 2 is good, the I square gives us the minus sign, and the k mu is there. So this looks good. Is this clear? I've checked the factors. I know the structure is this, and I check the factors quickly by Taylor expanding. Now, of course, by Taylor expanding this side, the first term just comes with a factor of 1, which matches that. Okay. So now I use this. I get e to the power minus I by 2. So this object was what? Now we've got e to the power minus I by 2. K mu I, K mu j. And this was minus 2 alpha prime log of sigma I minus sigma j. Oh. Sorry, I didn't have a I. Sorry, it's minus 1. It's minus 1. Okay, sorry. So I get minus 1. You understand, right? Because if you drop 2 powers of this term, the I squared becomes minus 1. That's minus 1. Okay, so I got this. And now once again I ignore the self-contractions. Same logic. So this factor of half goes away when I do sum over pairs. So this becomes product over pairs. Sigma I minus sigma j to the power 2 ki dot k. Alpha. Minus and minus. Say still the overall delta. Okay. And when we also now have to understand what happens to factors of del sigma x. The only derivatives on the boundary that can appear in vertex operators are the sigma derivatives. Because we already know that the tau derivative is 0. That was about it. Okay. So now we have to figure out what happens to del sigma of x. So we have to redo that calculation using the corrected Green's function. It takes a factor of 2. I'm just going to, so that the insertions of such things will once again be what you get from saddle point plus what you get from plus fluctuations. For the saddle point value, I'm just going to write down the answer. Same thing that we got before, with the carefully keeping track of the factor of 2. Okay, and here, the effective saddle point value is minus 2I alpha. I think we had minus some k mu I sigma minus sigma. Okay, so there is sigma x mu sigma. Is this plus its fluctuations? If somebody can look back into your notes and see what do we have last week? We had with what factor was this minus I alpha prime by 2. By 2. So that's that relative form. It's the relative form between. So, okay. So now we we have all our technicalities in place. I should say I've cut a few corners in these derivations. For instance, you could actually try to do all these derivations really on the sphere, keeping track of infinity carefully. That will, in a more satisfying way than I mentioned, give you the delta functions from the sequence. Okay. And you could wonder about whether there could be trouble from thinking of the sphere as patching together two planes and something with infinity. Polchinski has 2 or 3 very careful derivations of these things. Okay, I'm not going to bother to go into all of that, simply because the final results are intuitive, easy to motivate, and they're correct. Okay, but I urge you to read the parts where he has 2 or 3 careful ways of checking that this is the right answer for all our insertions. Of course, there's nothing to it. It's just Gaussian. We're doing some Gaussian stuff. There's nothing to it. I'm not going to belabor these results very much. We got the answer. It's reasonably straightforward. Okay. Fine. Now that we've got all the technicalities in place, we can finally start doing a calculation. Okay. So let us first try to compute the scattering amplitude. Oh, one thing before that. I should tell you about the mass shell condition for open strings. When you do the quantization of the open strings, you get, of course, a mass shell condition. The mass shell condition comes from equating the Hamiltonian to 0. So in the Hamiltonian, of course, we have the oscillator contribution, this n. And we had -1, that we always have. That's 1 plus 2 plus 3 plus 4 is equal to -1 by 2. That gives us the -1. Okay, but for the closed strings, let's remember we also had the zero mode. Now let's remember how it came to the closed strings. We had 1 by 4 pi alpha prime del square. So if we're interested in zero modes, we have constant in sigma. We can just do the integral over sigma, so this became 1 by 2 alpha prime. That's 2 pi square. And then this becomes just x0 0 dot square. And this is now the Hamiltonian of non-relativistic quantum mechanics with an effective mass 1 by alpha prime. So we get p squared by 2m. So we got alpha prime p squared by 2. And then we broke that up into half that went for the left movers, half that went for the right movers. So alpha prime p squared by 4 came for the left movers. And so we got alpha prime by 4 m squared is equal to this. This was our mass shell condition for closed strings. Okay? For open strings, there are 2 differences. The first difference is that when we do this integral, it goes from 0 to pi, not to 2. Of course, choosing 0 to pi was a convention. But it was the convention that ensured that this part of the Hamiltonian will still be n. Because the effective oscillator lives on 2 pi. Cosines are moded the same way. Okay? The second, so we get an extra factor of 2. The second thing is that there's no, we do it in this doubling way, there's no left mover, right mover. All of the Hamiltonian is for the effective left mover. Okay? So we don't break this up into some left moving, right moving sector. Okay? So there's another extra factor of 2. So the mass shell condition is alpha prime m squared is equal to n minus 1 for the open strings. So the tachyon, which has mass 1 over alpha prime for open strings, and mass 4 over alpha prime for closed strings. Mass square. So there's mass square difference of a factor of 4. The open string tachyon and the closed string tachyon.
Okay. Your mass is, what is it? Shouldn't it be the same?
What? No, why?
Your mass is 2 by about alpha prime by 2. Right?
You're saying the 2 factors of 2 go the same way?
Can
No, I don't think so. Let's see. Let's work out the open string now. Okay, so here what will we get? We start with the same action. We will get 1 by 4 alpha prime. Okay, x dot square, x0 dot square. Now the effective mass is 1 over 2 alpha prime. So 2 alpha prime by 2. Okay, great. Great. So I said this because now you can compute the open string spectrum. It includes also an open string tachyon. It also includes master states, and n equals 1. What are the vertex operators for the master states? The vertex operators for the master states are simply del x of sigma times e phi. Okay. These are the vertex operators for the master states, and the physical interpretation of these master states will be a photon. Okay. So just like in the closed string sector, the master states had gravitons. In the open string sector, the master states really had photons. Okay, so when you include open strings, in addition to the tachyon, which is subjunct, which will go away when you look at the superstring, you've got photons, gauge fields, moving around in space. Okay, just like closed strings give you gravitons, the open strings give you gauge fields. This is a chain to this. Okay, and the null states associated with these operators. What's null, by the way? Null is when this is a descendant, right? When is it a descendant? It's a descendant when it's del sigma of e to the phi k dot x, which is equal to k mu del sigma x mu phi k dot x. So this del x mu came with a polarization tensor, C mu. And the polarization tensor was equal to k mu. This is a descendant, so it's a null state. Okay? And these null states are pure gauge states. Pure Maxwell pure gauge states. So everything we said about gravitons, this is just half of that. And gives you equivalent statements for Maxwell gauge fields. Okay? So the open string sector is open strings are basically are as tightly tied to gauge to gauge fields as closed strings were tightly tied to gravitons. Okay, excellent. So now, though, let's retreat from these interesting but more involved gauge bosons. First, look just at the tachyons. Okay, so we'll do the scattering of both 3 open string tachyons as well as 3 closed string tachyons, just to make sure we get everything completely right. So what was the rule? The rule was that if we want a scattering of 3 tachyons, what was the rule on the sphere? Okay, let's first do closed strings. What was the rule on the sphere? The rule on the sphere was that 3 vertex operators have to be fixed. If we're scattering 3 things, then all have to be fixed. That's great because that means you don't have to do any integrals. Okay, so computation of three-point functions is very, very easy. Okay, let's first do it for closed strings. We'll do it for open strings, for the tachyons. So, suppose the momenta e to phi k1 dot x and some z1 e to phi k2 dot x being set with some z2 and e to phi k3 dot x at z3. These are 3 bulk points. We want to compute this times we want to compute c of z1, c of z2, c of z3 times c bar with everything sort of. Because our fixed vertex operators are c bar times the 1, 1 operator. Okay? Now, one of the checks of all of this is that if everything is working out right, the answer should not depend on what Z1, Z2, and Z3 is. This allows me to draw up the checks already. So let's do this. This guy, we knew how to calculate it. This was Z12, Z13, Z23 times bar. What about these guys? Well, in the early part of the lecture, we learned how to do it. We got that they were Z12 to the power K1 dot K2 alpha prime. Z13 to the power alpha prime K1 dot K3 and Z23 to the power alpha prime K2 dot K2. Is this clear? Okay, so the final result is Z12 into 2 plus alpha prime K1 dot K2 and 3 such factors. Now, how is it that this doesn't depend on Z12? Looks like it depends on Z1, Z2, Z3. Actually, it doesn't. It doesn't because K1 dot K2 is not something arbitrary but something real. Why is that? So K1 dot K2, 2K1 dot K2 is equal to K1 plus K2, the whole thing squared, minus K1 squared minus K2 squared. But all three states that was scattering, K1 dot K plus K2 is K3, minus K3 because momentum was. All three states that we are scattering are states that are tachyons. What was the tachyonic condition? What was the condition for tachyons? The condition for tachyons was that K squared, now we have to get this right, we're using mostly positive. So K squared is equal to plus or minus, just a minute. K squared is equal to plus because it's tachyons. So is equal to, we got 4 by alpha prime with a plus. Let me just check that was plus. Yeah, because it's mostly positive. I think that's right. Okay. So each of these is 4 by alpha prime. Okay. So this is 4 by alpha prime minus 4 by alpha prime minus 4 by alpha prime. That's 2 K1 dot K2. Okay, and therefore 2 alpha prime K1 dot K2 is equal to minus 4, and therefore alpha prime K1 dot K2 is equal to minus 2. So each of these powers is actually 0. Is this clear? Is this clear? It's just a number. This scattering amplitude is just a number. Now let's think a little bit about this number. You see, the scattering amplitude, what was it? It wasn't the expectation value divided by partition function. It was the full path integral with these guys inserted. Okay, so you see this path integral has a lot of undetermined stuff. Because there's the determinants, there's the non-zero, the ghost determinants, there's the determinants from the scalars. Let's call that whole thing, all the determinants are grouped together to call it determinant on S2. Plus, you remember that we decided that we would add this term that was G times integral R over the Riemann surface. Let's call that G naught. So I get G naught times integral R. So I get G naught to the power minus 2 as well. Okay? Times a particular number, and that number is just 1. Now, what we will keep track of carefully is relative factors. Okay? Because we don't know what this determinant is. We don't, this G naught is something. But we do know that the determinant is the same for every sphere population. Okay? So while the absolute values of these guys are tough to compute, can be done actually with careful calculation. Okay? While the absolute values of these guys are tough to compute, the relative numbers are easy to compute and are meaningful, and we'll keep track of them. Okay? the 3 tachyon scattering just gave us, what was the summary? Just gave us determinant times g naught to the power minus 2, the factor of 1. Now, firstly, why is it reasonable that 3 tachyon scattering is just a number?
So every time you're talking about these scatterings, you actually have the Y field in mind, right? But because otherwise,
The what?
The Y field that we described, that we define to be otherwise open strings will not have.
Yeah, so far we've been talking about closed strings. Okay, when we talk about open strings, you can think of the Y field or just do the path integral of the upper. Actually, the way we're going to do it is just do the path integral of the upper.
For scatterings, you want to get closed intermediate surfaces which are with fixed 158 only that.
Our rule is you have to compute some insertions of operators. The rule is that gives you the S matrix.
Insertions of operators on these closed surfaces, right?
Closed surfaces or insertions of operators with boundaries on surfaces with boundaries. Just that's the rule, and that's what we're going to do. Okay, good. Now let's quickly see that we get the same answer, same kind of answer for it. Before that, why is it reasonable that we got something that was just a number? Well, actually, what else could you get? You see, there are no because we're looking at a scalar. There are no polarization tensors. So the answer can only depend on the 3 momenta. Has to depend on the Lorentz invariant. The only Lorentz invariant structures you can form are K1.K2, K1.K3. But all of them are completely determined as we see by kinematics. So there's nothing it could have depended on. The scattering of 3 scalars is necessarily just a number. Again, it's not a function of momentum. It's not a function of polarizations. Things will be a little more interesting when we include gate bosons.
One more time.
One more time. One more time will give much more interesting. Yes. Okay. But of course, there's still information in the value of this number. Okay. Now let's move on to the open string tachyons. What did we get from the coast? There we got y12, y13, y2. Because just one coast, now we use the doublet trait, blah, blah, blah. Just one coast, it's not getting 2 of these coasts. What about from the x's? You remember that the rule was that we got y12 times, was it 2 alpha prime? K1 or K2, can somebody check? So we get y12 to the power 1 plus 2 alpha prime K1 sub K2 and a product of 3 such terms. Now the question is, what is K1.K2 for the open string tachyons? But we figured that out. We knew that K1 squared, K2 squared, K3 squared, each of them is 1 over alpha prime. Okay? So K1.K2, 2K1.K2 is minus 1 over alpha prime. So K1.K2, so 2 alpha prime K1.K2, so minus 1 over alpha. Perfect. Goes away. So the modified mass shell condition for the open string tachyons conspires together in such a way so that the positions from host, position dependence from hosts, cancels the position dependence from the tachyon. Okay, excellent. Now we want to compute a few more free scattering, three object scatterings. Okay, before turning to the really interesting bit, just 4 object scatterings. Okay. But it's nice to do the 3 object scatterings first because they give us preparatory information that will allow us to interpret 4 tachyons.
case, we don't think that the moduli space of integral of the moduli.
There's no moduli space. We're on the sphere or the disk, which is no moduli. And we don't even have moduli space associated with vertex operators because we just got 3, so all of them are just fixed. So there's no integrals. Okay, this is like the analog of Lie. Yeah, it's really simple. It's really simple. It's the best kind of calculation, right? The kind that you can do with 5 or 10 minutes. Okay, but of course it ensures that you can't get anything too interesting. You need some structure and something interesting. So once you have 4 insertions, 3 of them will be fixed, but 1 will be integrated. And it's that integral that will give you everything. Okay, fine. Now I'm going to start computing. I'm going to start computing the scattering of 2 tachyons with a gauge. But in order to do that and get something interesting, I need to introduce a physically very relevant and a generalization of the open string discussion. Okay, to include these things that are called Chern pattern factors. So what are Chern pattern factors? We've got our strip, which is the open string. Okay, and let us assume that there are boundary degrees of freedom living on the strip that are dynamically inert. Okay, so let's suppose that there is a vector space worth of degrees of freedom, okay, living on every boundary of the open string. Okay, this vector space is finite dimensional vector space, runs over n values. So in order to specify your state of the open string, to specify what the string is doing, plus what the boundary degrees of freedom. Okay, so another way of saying it is that there are n squared different open strings. Okay? In order to specify these open strings, you have to specify where in the first n-dimensional space you're living and where is the second n-dimensional space you're living. Okay? So you give a polarization, in this color space, some polarization tensor, some alpha I.
N is not the usual spatial dimension.
N is totally unrelated to spatial dimension. We will actually see what N will have to be for consistent open string theory. Because that will be 32. Hang on.
Yeah, I don't understand. What do you exactly have at the boundary as degrees?
What do you have at the boundary? Okay. What we've got is a little Hilbert space here. Okay? And the Hilbert space has no dynamics. If you've got a state in that Hilbert space, it does not change. It does not change with time. So you just imagine that your system is a tensor product of 3 dynamical systems. There's the system in the bulk. There's a Hilbert space living here and a Hilbert space living here. Okay? These 2 Hilbert spaces are just totally inert. Whatever you sit in a particular state at the boundary, you will stay there forever. It's not interacting with what's going on here. It's just like almost a spectator. Okay, I know this sounds very ad hoc. Hang on for a little bit, it'll feel less ad hoc as you go along. You guys actually you guys are studying these boundary states, right?
Yeah.
So there's a boundary degree of freedom. Okay, let's just go on for now. As we proceed, you will find ways of saying this that sound less completely ad hoc. Okay? Let's go on and see what happens. Okay.
Just to be sure,
Yes.
it has nothing to do with the boundary conditions on that we impose on the open.
Yeah, the boundary conditions. We're doing something very, very simple. we're taking these boundary degrees of freedom and there's no interaction between the boundary conditions and these boundary, or we're totally decoupling what's happening, the bulk and this boundary. So, no. You can do more sophisticated things. Okay? You can invent boundary conformal field theories with real, genuine degrees of freedom living at the boundary, where they interact with what's going on in the bulk. And that's an interesting game. Okay, here we're looking at the most trivial example of that game. Because just nothing happening basically. From the point of view of conformal field theory, what is so trivial you won't even bother to consider it. Because just nothing's happening. Okay? But this will lead to a nice natural generalization of string activities. This triviality will give us something sort of interesting. Yes?
Suppose we had something where a open string split into two and then joined again, then you'd have the sum over things like the truth counting.
Exactly. That's where we're going. Exactly. So, now if you specify an open string, you have to specify two things. You have to specify the vertex operator. But you also have to give me an n cross n matrix. Okay? Which tells me what my state was in the basis of this auxiliary Hilbert space and this auxiliary Hilbert space. Okay? So suppose I have the states in this are labeled by a basis I runs from 1 to n. The states of this are labeled by some basis j runs from 1 to n. This is the most general state you could have summation implied. Okay? So you have to specify both the state in this auxiliary Hilbert space where nothing is happening. Okay, I think we call it lambda. Okay, and the state in the bulk where all the fun is happening. Okay, which we've already done. Okay. Now, so suppose I've got an external state. It's specified by a lambda ij and a k. Let's say an external tag. Okay? It's specified by a lambda ij and a k. Okay? And so I've got my lambda ij and my k. And now what I have to do is to look at all possible. I want to compute the scattering of 3 tachyonic states specified by k1, k2, k3, lambda 1, lambda 2, lambda 3. That's what I'm going to try to do. Okay. Now let's first look at this. We've got this disk, and we've got these open strings coming into the disk. Okay. This guy has some particular ij. That's specified by this lambda. This is the state lambda ij. But we said that along the boundary nothing happens. So wherever was this I was also this I. Wherever was this, and so on. So do you see that 3 of these insertions now when we put them into insertions like this? I sometimes draw this as a disk, okay? This disk is conformal to the above. When we put them into insertions like this, you see that the extra factor we're getting is trace of lambda 1, lambda 2, lambda 3. Exactly. These are going to be interpreted as counterfeits. Enlarging this open string Hilbert space to include these n cross n will of course give us n squared photons instead of 1 photon. Because any ij combination gives you a mass. And what we're going to see is that this will give us non-abelian photons. That will be the miracle of it. UN non-abelian photons. Okay? But first let's go slow. So we've got this trace of lambda 1, lambda 2, lambda 3. You see this, right? Because the fact that nothing happens means the indices are just conserved elements.
But you will not get the full trace if you map the disk to the upper half plane.
Oh, but the upper half plane was, you see, when we were doing string scattering, we always really were doing the sphere. The plane was just a conformal representation of the sphere.
So you always do that.
Yes, this here we were always really doing the disk. That's how you should think about this. Right? Okay, so now There's something when we looked at the open string tachyons, even without these insertions.
So lambda 1 and lambda I index on.
What?
You've got one index on lambda that I got a little confused with these.
In lambda is a matrix.
Okay.
It's like this.
How do you look at this picture, like the conservation of this color, from the point of view of the upper? I mean, this can be.
It's just that at infinity it's so now. Here you've got some vertex operator. Here you've got so here color flows, it's conserved. Here color flows, it's conserved. Here color flows, it's conserved. But it's also conserved at infinity. You don't see that, but you will see it once you map this to the disk. The upper plane is always just some representation of the disk. Convenient representation.
Okay. Lambda 1, lambda 2, lambda 3 are they're the same thing.
What?
They're same
No.
matrix.
No, could be different matrices. You see, you've got one tachyon which is in one state in this auxiliary n cross n element space. Another tachyon which is in another state. Third tachyon, third
But
state.
the whole matrix is same. It's a different element in that matrix.
You see, this is choosing a particular vector in the Hilbert space.
Yes.
The guy with momentum k1 has one vector in the Hilbert space. The guy with momentum k2 has a second vector in the Hilbert space. The guy with momentum k3 has a third vector in the Hilbert space. Lambda 1, lambda 2, lambda 3 are three distinct n cross n matrices. Just like k1, k2 and k3 were three distinct momenta. You're choosing which guys to scan. Okay? Okay. Now, there's one more thing here that will turn out to be, and that's this. Look, we've got this disk, and we've got insertions of these three guys. Let's say lambda 1, lambda 2, and lambda 3. Where we insert the vertex operators, okay, doesn't matter, as we've seen. We've already checked that the answer didn't care about the insertion points. Okay, but it will matter which relative order we insert the vertex operators. The idea here is that suppose you've got a certain relative ordering. The reason why the positions of insertions were not supposed to matter is that you could always move one position to the other by an unfixed diffeomorphism. But these unfixed diffeomorphisms, because they're one-to-one, cannot change relative ordering along the boundary. So, though we don't care about where these guys were inserted, relative orderings of insertions are diffeomorphism inequivalent and have to be explicitly summed over. So how many relative orderings do we have here? This is one, and the other one is lambda 1, lambda 3, lambda 2. They're just two cyclic orderings. 1, 2, 3, 1, 3, 2. So they're the same subcycle. Okay? And this was true actually, even without the Chantal factors. So when I told you that the open string scattering, I got the answer 1. I was secretly a little wrong. It should have been 2. Because there are two relative orderings. Okay? And here it becomes more serious because these two numbers are not the same. One of these is trace of lambda 1, lambda 2, lambda 3. And the second one is trace of lambda 1, lambda 3, lambda 2. As you see from the fact that we get the trace, only cyclic and relative cyclical ordering matters. These two things do matter. And in particular can be written as trace of lambda 1 anticommutative lambda 2, lambda 3. We'll see why this is useful later. Okay, what, sir?
You didn't have this relative ordering when you had a sphere as a...
Because there's no such thing as relative ordering in the sphere.
But now you have to cross two operators and you have...
Yes, you see, we're doing diffeomorphisms that do not change the location of the boundary. Such one-to-one diffeomorphisms cannot change relative orderings of boundary insertions. Because You see, on a line is different from a plane. And the boundary is effectively a line. Okay? Okay, now with all this preparation in hand, with this preparation all carefully in hand, we will now do the first calculation that will give us something sort of interesting. And the calculation we will do is to compute the insertion of two open string tachyons and one open string K2. Okay. It's a tricky calculation. There's a sign here that's tricky to keep track of. I hope you managed to keep track of. Fine. So we've got our gauge boson. It's got some momentum K1, and it's got lambda. This Chan pattern Hilbert space matrix structure lambda. And we've got our two cations with K2 and K3. Okay. All three are fixed vertex operators. So from the hosts we get y12, y13, y. Okay, so from the hosts we get this. Yeah, that's unchanged. What about from this stuff? Well, you've got del x at sigma 1 is pi k1 x1 plus k2 x of sigma 2 plus k3 x of sigma 3. Okay? Now, first let's do it roughly, and then we'll add the two contributions. See how that goes. Okay. So this is the expectation value we want to compute. We know the rules for the computation very well right now. Okay? Things are particularly simple when we've got just one insertion here. The reason for that is that the fluctuation field has nothing to contract against. So we can just replace that insertion by the saddle point value. Okay. So this guy is just replaced by minus 2i. Somebody will have to help me. Was there alpha prime or pi alpha prime? Pi alpha prime. It was some ki. So I'll just write it out. K2 mu. This is del of x mu. And let's say that there is a C. Okay. Keeping track of the polarization. So I C mu times K2 mu. Okay. I call this a D. That's what we know. K2 mu divided by sigma 1 minus sigma 2. Plus K3 mu divided by sigma 1 minus sigma 3. The cell contraction terms are omitted. So we get this. Okay? Times we get what? Times we get y12 mod y12. Okay? Times we get mod y12 into alpha 2 alpha prime k1 dot k2 into y13 2 alpha prime k1 dot k3 y23 2 alpha prime k2 dot k2. Right. Let's call these also y. So this is y12. This is y13. We've got this times this times y12, y13, y23. And if we choose a particular order, let's say we chose the order 1, 2, 3, we have trace of lambda 1, lambda 2. Now we have to process things. The first thing to process are these numbers. We're now going to get different values for these numbers than they did before. Why? Because K1 obeys the mass shell condition K1 squared is equal to 0. Not K1 squared is equal to 1 over alpha prime. So let's compute each of these. 2 alpha prime K1 dot K2. Okay, is equal to 2 is equal to alpha prime into K1 plus K2 whole thing squared minus K1 squared minus K2 squared. K1 plus K2 is K3. 3 and 2 are tachyons. K1 squared is 0. So this cancels this to get 0. So this is equal to 0. Yep. Similarly, 2 alpha prime K1 dot K3 is equal to 0.
So can you repeat the answer?
Yeah. So this is K3 squared.
Yes.
K3 squared comes from the mass shell, is fixed by the mass shell of the tachyon, which is the same as K2 squared. This is fixed by the mass shell of the gauge boson, but K1 squared was 0. Okay? So 2 alpha prime K1 dot K3 is also 0. But 2 alpha prime K2 dot K3, now that's more interesting. Because this is equal to alpha prime K2 plus K3 thing squared minus K2 squared minus K3 squared. This is K1 squared, so that's just 0. But each of these was 1 over alpha prime. So this is equal to alpha prime into minus 2 by alpha prime. It's equal to minus 2. Okay? So now let's correct the y dependencies so far. y12, y13, y23 times mod y12, mod y23 to the power minus 2. Okay? And we're left with this stuff. So let's look at that stuff. Okay? So this is minus 2i alpha prime E1 mu into K2 mu by y12 plus K3 mu by y13. Now, what do we know about E1 mu? E1 dot K1 is 0. What we have here is E1 dot K2 and E1 dot K3. But K2 is minus of K1 plus K3. And E1 dot K1 is 0. So E1 dot K2 is same as minus of E1 dot K3. Okay? We can write this as minus I alpha prime E1 dot K2 minus K3, just to be democratic between 2 and 3. Okay? Times 1 over y12 minus 1 over y13. Remove the 2 because I got 2 of these. Is this clear? And then I simplify this. This is equal to y13 minus y12, so that's y23 over y12, y13. Now let's look at the net powers of y23. There's one guy here, 2 in the denominator, they cancel. Let's look at the net powers of y12 and y13. These guys. So they cancel. Okay? So everything cancels, and the net result is that we got E1 dot K2 minus K3. Okay? Times trace of lambda 1, lambda 2, lambda 3. This is one of the two ordinals. Okay? And now is this tricky thing with the sign. The tricky thing with the sign has to do with the fact that some of these guys are y12s and some of these guys are mod y12s. Okay? So this is the kind of thing that thinking. Okay. And you have to be very careful. The thing that we're going to do now, so we've got either plus 1 or minus 1. And if it's, but that's not important. What's important is what is the relative sign between what we had here and what we have if we interchange, let's say, 2 and 3. Okay, so the point is that there is a relative bias. Okay. Now, this is of course the hardest kind of thing to keep track of. So let's see if we can understand that. Okay, everything here was genuine y12s. This here. Okay, we're on our own, and where do we get this sign? I have a suggestion. Let me ask you to hunt for the sign, and we'll clear it up next class. Yeah.
So, if you exchange 2 and 3,
yeah,
there will be a negative sign coming from the first term because y23, it will become y32, which is negative of y23. But this term, the last term, it will always be the same term, whether you exchange 2 and 3.
It will be y13 1 by y13 minus 1 by y12, and that will also become y32.
No. So it's just always 1 upon y12 plus 1 upon y13. If you exchange 2 and 3,
yeah,
it's the same term.
Yeah, this might be it. This might be the sign. This might be it. I'll confirm this after I've carefully thought about it, but that sounds right. Yeah. Okay, so The net result, when you think about this carefully, you get E1 dot K2 minus K3 times trace of lambda 1 into lambda 2 commutator lambda 3 because of the minus sign. Now, why is this an interesting answer? Can somebody tell me why this is an interesting answer? What effective field theory would give you 3-point scattering, this 3-point scattering? You write down an effective action that will give you this 3-point scattering. I'm writing it up. Take the tachyon, it's an android field. Minimally couple it to the gate boson. What is minimal coupling? Minimal coupling means this is d mu plus I a mu t mu. Okay, so let's look at the 3-point function. The 3-point function comes in one of these things. And one guy here which is just derivative of t. So the 3-point function comes from this trace of d mu t times a mu t. Okay? Now, let's look at this. Let's look at what we will get from it. Okay? Let's look at what we get from it. Here we get a derivative that runs in one of the tachyons. Okay? But because this polarization index is orthogonal to itself, it doesn't matter which tachyon momentum you use. So the derivative that runs in one of the tachyons will give you either K2 or K3, depending on which one. But actually it doesn't matter for the same reason that we discussed. Because this is going to be contracted with the polarization index. The polarization index is orthogonal to K1, and therefore polarization index for K2 and polarization index for K3 are the same thing. So this structure will give you polarization index dot either K2 or K3, doesn't matter. Might as well write as K2 minus K3. And then this structure will give you this trace. So do you see that the amplitude that we produce is precisely the 3-point amplitude that you get by minimally coupling the tachyon with the gauge field using the fact that the tachyon, like every other field in the matrix, they're all matrices, are in the adjoint representation. Do you see this? Okay. Now, the last 3-point function I'm going to ask you to compute is one which involves 3 dimensions. It's very similar to the calculation that we've done. Except that now you have 3 downstairs insertions, 3 dexes. Okay? So you have to carefully take into account A, the classical parts of all of them, and B, also the quantum parts. And then pairwise these y's will contract. So there will be terms where you take all 3 classical contributions. And there will be terms where you take 1 classical and 2 quantum contributions. Okay? I'm going to leave this as an exercise for you, which I'm going to ask you to do by next class. By the way, our classes are now Tuesdays 2 p.m. and Thursdays at 11:30. Okay? Rajdeep has kindly agreed to do this class for me as Tuesdays. Okay? So, okay, I'm going to ask you to try this calculation yourself. Okay? What should you expect from the answer? One of the terms you should expect from the answer is the term that comes from? So these are very gauge bosons, there should be such a term in them. Okay, and there may be other structures that you get. You see, on-shell 3-point functions are largely fixed by domains. Okay, so if you're getting something that's consistent with gauge symmetries, this guy, maybe one or two other structures are possible. Actually, there's one other structure that's possible in this case that comes from some higher derivative contribution, some higher derivative kind of interaction. Okay? In the bosonic string, you get both of these. Okay? So that's the thing I want you to check. I want you to do the calculations, see that all the z's cancel out, the y's cancel out, and then get the final answer and interpret it in terms of space-time structures. Okay? I'll leave that as an exercise for you. It's a bit too involved to do in class. Put many things together and you don't gain much from it. It's something you should do yourself. The principles are now clear, right? What is being done? Yeah? Okay. So I think this means we'll stop today's class here. By the way, we should also do 2 tachyons and 1 gravity. 2 close string tachyons and 1 gravity. And then of course 3 gravity. Okay, I'll also ask you to do this next. Next 2 opens, close string tachyons and gravity. That's about as easy as that actually. Because it's just it's more or less the same calculation. Two copies of the same calculation. Okay, and then I'll ask you to do that as well. And to verify that comes, the interaction is that minimal coupling to gravity of the tachyon reproduces that thing. Okay? Good. So we will modulo the fact that you guys have to do these exercises. We will close our discussion of 3-point functions. The really interesting scattering, in our course, there will be like a few highlight formulae. One of them was that beautiful formula for the stringless matrix. It's one of the most important formulas. We're coming in the next lecture. We will talk about one of the other most important formulas, namely the explicit formula for 4 tachyons contained, both of the closed and the open string. You see, this explicit formula is such a remarkable formula. Really, it's supersymmetric generalization. Okay? It's supersymmetric generalization. It's such a remarkable formula. It's so remarkable that I believe that there is no counterexample to the following claim. That if you search for a scattering amplitude that you demand is purely classical, that has only poles, no cards, that dies off, that reduces at low energies, scattering amplitude of gravity, and that dies off at large energies. Okay? Unitarity is, if it didn't, it would mean strong attention to unitarity. So anyway, for that reason, suppose we search for a scattering amplitude that has these properties, and that obeys unitarity, so that the coefficients of all the poles are all positive. Okay. So the question is, can you find any scattering amplitude that has all these features? Maybe we need to add one or two more features, causality. Can you find any scattering amplitude? Bring it out of your head if you want. Find any scattering amplitude that obeys all these features. I believe there's no counterexample except perhaps very trivial to the claim that the only solution to this problem is the only solution anyone's ever written about this problem is the formulas, the supersymmetric generalization of the formulas we talked about. So it is possible that this is the first road in life of string theory. String theory does generate the only known consistent classical generalization of Einstein. Einstein gravity. And it could be that it's the only one. For that reason, and the formulas we talked about next class, the Veneziana, Peter Shafira, are the formulas that these people just came upon, more or less by trying to address the question that I posed. They just, by looking at functions, came upon this function. That started the study of string theory. And 40 years later, we don't have any other examples of a formula that does what they wanted to do. Of course, understand these formulas from our point of view very well. There's no other example. It could be that they need. Okay, and then certainly it would be one of the few most important formulas. Okay, yeah, so.